In this mini lecture, we are going to talk about the drag force. Drag forces are resistive forces. They always oppose the motion of an object, just like friction. You can think of it as kind of like friction against an object and a surrounding fluid. Air is a fluid. Drag forces occur on an object when it moves through the fluid or liquid or gas. The magnitude of the drag force, so its size, is proportional to the square of the speed of the object. So this is the equation for drag force, and you're just going to have to take my word for it that this is what it is. We're not going to derive it, and I'm not going to show you how we're going to find it, but we might do that later when we talk about fluids. But here we've got the drag force. I always put a little sub d for the subscript on the drag force. It equals to 1/2 times c. C is a drag coefficient, kind of like our coefficient of friction. And it varies for the shape of the object, and it could also change for the speed of the object or properties of the surrounding fluid. This quantity C has to be determined experimentally, just like it is for the coefficients of friction. And then we multiply it by this Greek letter rho, which represents the density of the fluid through which you're moving. A is the cross-sectional area. It's the cross-sectional area of that body perpendicular to its direction of motion. So if, let's say, okay, here I have my cell phone. This is my cross-sectional area A, the side of my cell phone. So if my cell phone, if I drop it like this, flat like this, drop it toward the ground, this cross-sectional area A would be the area of my phone that's exposed to the fluid as it's falling down. So that would be what I use for my cross-sectional area, okay? And then V, that's the speed at which the object is falling down or moving. It doesn't necessarily have to be falling. V is the speed at which your object in question is moving. And you square it. Here are some examples of drag coefficients. Remember, they have to be determined experimentally. Here's the drag coefficient for an airfoil. That's like kind of like the wings of an airplane. So you see it's really small. It's designed specifically to reduce as much drag as you possibly can. We've got a couple other drag coefficients for some cars. So Hummers are these big brick cars, right? They have a large drag coefficient. Bicycles have a pretty large drag coefficient too. Skydivers, horizontally, so if they're laying out flat when they're falling through the air, they have a larger drag coefficient than when they're upright, when they're falling upright with their feet first. It all has to do with sort of the shape of the body and how much of that area, cross-sectional area, is going to be exposed to the fluid as you're moving through it. Here's some more examples. You can see the shapes of these bodies and their drag coefficients. And again, these have to be determined experimentally. You can just read them off of a chart. So terminal speed is an important concept that we're also going to be talking about here when we talk about drag. Now, just after an object is released from rest, its speed is low and the drag force is small. So as it falls farther and farther, its speed and therefore its drag force increases. So remember, the drag force was proportional to the velocity of the object squared as it's falling, or the speed of the object squared as it's falling. At some point, we know when we were studying one-dimensional motion that when you release an object from rest, its speed is going to increase as it gets closer and closer and closer to the ground because of the acceleration due to gravity. So when an object is falling through the air, its speed is going to increase and increase over time. That means that the drag force is going to increase because it's proportional to the square of the speed. But if you're moving through a material that has a non-zero density, there's going to be a speed at which you can exactly balance the upward drag force acting on the body and the downward force of weight. So when you reach a condition where the drag force pointing up and the weight of the object pointing down exactly equal to each other, then you are in equilibrium. The upward force and the downward force match each other. And whenever you're in equilibrium, then that means that your acceleration becomes zero and you reach a constant speed. that is your terminal speed or your terminal velocity. So here we have a depiction of this. We've got a ball that's just released from rest. Okay, so it's traveling downward at a low speed right now. It's falling at the constant acceleration of 9.8 meters per second squared. We've got its weight vector pointing down, small drag force opposing the motion. But eventually, as that object continues to fall, its velocity or its speed is going to increase. V will reach a value such that the drag force exactly equals or balances the weight, the component of weight pointing down. Then the net force, the sum of the drag force and the weight, will become zero. The acceleration is zero. The ball falls at a constant speed. That speed at which this is occurring is our terminal speed or our terminal velocity. We're going to derive the equation for terminal velocity here. And we're going to think about this problem when we think about a cat falling off a building.
In this problem, we're going to think about the terminal velocity and drag force acting on a falling cat. So we have a cat that's going to jump from the top of a very tall building ledge. Okay? The falling cat reaches a terminal velocity of 97 kilometers per hour while it is tucked in. Okay. Then all of a sudden it decides to stretch out its legs, okay? And it doubles its cross-sectional area that's exposed to the air as it's falling vertically, okay? And so then we want to find how fast is it falling, what's its new terminal velocity, how fast is it falling when it reaches a new terminal speed now that it's stretched itself out and it has twice the area perpendicular to the direction in which it's falling. Okay, so cat's here and then it stretches its legs out, changes its terminal velocity, and we want to figure out what that new terminal velocity is. All we know is how fast what its initial terminal velocity was achieved, and the fact that it eventually spreads out to twice the surface area exposed to the direction as it's falling vertically downward. Okay, so if we think about the free body diagram of the cat, it always has its weight downward, its mass times gravity downward. It's got a drag force opposing this motion. This drag force coming from the fact that the cat is falling through the air. Okay, and objects always reach a terminal velocity when their acceleration becomes zero. Okay, so that can only happen if you're falling through a medium that's not a vacuum. The acceleration is zero in a situation where you achieve terminal velocity. Okay, so let's write down Newton's second law for our cat here. So we're just moving with vertical motion, so the sum of the forces in the y direction equals our mass times acceleration in the y direction. Once we reach terminal velocity, we're not accelerating, so this is zero. So you have the drag force upward, the mass times gravity downward, and that equals zero. And we had our equation for the drag force, which we saw, which was 1/2 times our coefficient, our drag coefficient, times the density of the material through which we're falling, times the cross-sectional area of that object perpendicular to the direction of motion, times the terminal velocity squared. Okay, that's the drag force. And then minus mg equals 0. So if I solve this equation, I'm going to solve this equation for the terminal velocity. We're going to solve this and essentially derive the equation for terminal velocity in the process. So I'm going to move mg to the other side. I've got 1/2 coefficient of friction, rho, cross-sectional area, terminal velocity squared equals mg. If I multiply both sides by 2, I get rid of this 1/2 over here. So I've got c rho a terminal velocity squared equals 2mg. Divide both sides by c rho A. V terminal velocity squared is equal to 2mg over coefficient of drag for the drag coefficient, density of the material through which we're moving, cross-sectional area of that object. Okay, now square root both sides. So if I square root both sides, I get rid of the square on the terminal velocity. So here's our equation for terminal velocity. Terminal velocity is equal to the square root of 2 times mass times gravity divided by the drag coefficient, density, cross-sectional area of the object. This is the density of the material through which we're moving. That would be air in this case. We've got the equation for terminal velocity. If we do the same thing for our cat when it's outstretched, we will find we'll do exactly the same process. The only difference is that the only difference for our cat that's stretched out here in the second part of the problem is that the area is twice that of the original. So I'm going to call the cross-sectional area of the original cat tucked into a ball, call that A sub 0, A sub naught. If I solve this equation exactly again, but for the terminal velocity now, once the cat is stretched out, I'm going to call that V sub T2 for the second part of our problem. That terminal velocity will equal to the square root of 2mg over coefficient, drag coefficient, density of the material through which we're falling times 2 times the original cross-sectional area. Because our cat is going to stretch out, reach a new terminal velocity, and when it does that, it has twice the cross-sectional area that it did originally. So I just swap out here A naught for 2 times that original cross-sectional area. And then you see here that the 2 and the 2 cancel. So my terminal velocity for the problem when the cat stretches out to twice its original cross-sectional area, that terminal velocity is equal to the square root of mg over c rho A naught. Okay, a little bit different by a factor of the square root of 2. Okay, so let's take the ratio of both of these quantities and see what happens. So if I do that, I'm going to do the terminal velocity of the cat when it's stretched out over the terminal velocity of the cat originally when it's tucked in. So that's going to equal to, on top, we've got the square root of mass times gravity over c rho cross-sectional area, divide it by our original terminal velocity, which was the square root of 2mg over c rho A naught. Okay, everything is the same except for this square root of 2 on the bottom. Okay, so I could rewrite this bottom part as, I could pull out the square root of 2. I could say that this is the same thing as the square root of mg times square root of mg over c rho A naught times the square root of 2. So I just pulled out that square root of 2 and just moved it outside here so that it's in its own radical. Okay, and then I see that this term is exactly the same as this term. We're assuming also in this situation that the coefficient of drag doesn't change between when the cat is tucked in and when the cat spreads out. Okay, and that the density as the cat is falling, the density of the air isn't changing substantially, so that all of these terms are the same. Okay, so then we're left with the ratio that the terminal velocity when the cat is stretched out over the terminal velocity originally for the cat is equal to 1 over the square root of 2. Okay, 1 over the square root of 2 is also about 0.71. So then we see that the terminal velocity of the cat when it's stretched out compared to the terminal velocity of the original cat equals 0.71. So I multiply both sides by our initial terminal velocity, then that cancels over here. So now we have an equation for the terminal velocity of the cat when it stretches out is equal to 0.71 times the original terminal velocity. So here we derive the equation that we need to solve. Okay. So when the cat stretches out to twice its area, it's going to have a smaller terminal velocity. That's what this equation says right here. Okay. So if I take 0.71, which is 1 over the square root of 2, times our original terminal velocity of the cat, which was 97 kilometers per hour, 0.71 times 97 kilometers per hour, then I find that the new terminal velocity for the cat is 68.6 kilometers per hour. All right, so that's how we can compare these terminal velocities. So whenever you increase your cross-sectional area exposed to the material when you're falling and eventually reach your terminal velocity, whenever you increase that area, you end up decreasing your terminal velocity. Why? Because you have a larger drag force. Whenever you increase your cross-sectional area, that larger drag force is going to want to oppose your motion.